Good evening. Last time we have worked out the K-calculus to evaluate the proper time with this different new approach. Now we use the results obtained last time to find out how to add the velocities in special relativity. Let's start with the same simple consideration. Consider a situation like this where we have a person standing still on the ground. This is the with the label A. Then we have a tank. Moving in this direction with velocity v with label B. And then we have a projectile traveling in this direction with velocity u relative to the tank. So u is the speed at which the projectile, the bullet, exits from the mouth of the gun. And this is the object C. Okay, you know that in the simple approximation of Newtonian mechanics, when the speeds are all much less than the speed of light, we can simply say that the velocity of the bullet as seen by the man A is just simply the sum of the two velocities v and u. So if we call w the velocity measured by the man, we can simply write that w is equal to v plus u. That's all. That is very simple, trivial, and it is for sure true for all the velocity that we normally see and measure on the Earth. So for all the problems involving ordinary motions, this is perfectly valid. We can use this formula also for bodies moving in the space at velocity that are just only little fraction of the speed of light. But the situation changes drastically when we consider relativistic velocities. Let's see what it happens. So this time we have to consider this new situation. Using the K-calculus. Okay, we know that the word line of the man A is just the vertical T line. So this is the situation of our standing still. This is the position, no? And this is the time. So A is standing still here, and the word line is this. The time passes, but the man continues to stay in the same fixed position. What about the tank? It moves with velocity v. Remember that 45 degrees line is just represents the speed of light. So the tank moves with the velocity v, and this is the tank. Then what happened? And this is this angle here. I mean this the slope of this straight line is correlated to the velocity of the tank. What happens then? That the speed of the bullet is this one, so that u is the velocity of the bullet relative to the tank, and this is v. Okay, so suppose that I consider a small time interval, the time of the man here. How can I calculate the segments on the line of B and C? Simple. I consider the light lines, 45 degrees, like this, and like this is not 45 degrees, I'm sorry, this is 45 degrees, one, and so that I find that the segment, little segment A corresponds a little segment B on this line, and a little segment C on the other line. And what we know from the K calculus, we know that B is equal KAB, where with AB I mean these, I represent the K corresponding to this displacement, okay, times A. So the segment B is equal to the segment A multiplied by the K factor AB. But then I can write also that C is equal K BC B, considering this angle. Then the last equation that I can write is that C it is also equal to this displacement here. So it is equal to K from A to C times A, little a. Okay? Well, now with these three little equations, I can combine them, because using the last two, I can write that. The first two. From this first two, I know that C is equal to K BC times B, but B is equal KAB times A. So from these two, I get this one. But C is also equal to this. So at the end of the day, I can write that KAC times A is equal KBC KAB times A. A goes away, and I've got this final important equation. Okay, let me write it here. KAC equal KBC times KAB, so that I can cancel a bit. But now, remember what K is. From the last time, we discovered that K is equal to we use this one. We found that K squared is equal to C plus B over C minus B. Okay. Now, what is KAC? KAC is the speed of the bullet as seen by A. KAC. That is W. The speed. So we know that KAC square is equal C plus W over C minus W. KBC square, we must use the velocity of the bullet C as seen by the tank B. So it is U. And the last one, KAB, square, KAB square is the velocity of the tank as seen by the man A. That is V. So C plus B over C minus B. These are the squares of K's. And so I can write this equation in this way. KAC square is equal to KBC square times KAB square, squaring all the terms, from which we have that C plus W over C minus W is equal to C plus U over C minus U times C plus V over C minus V. Okay? Good. So we have to work a bit with algebra in this equation here. Okay? Well, let's call, as you see, we want to calculate W, that is the speed of the bullet as seen by the man A. So it will be a function of the other two velocity, u and v. So we can call this right member lambda uv as a function of the two variables u and v. Let's call it lambda for simplicity, whatever it is. It is a number. It is a number depending on the value of u and v. Okay, let's call lambda. So we have got that c plus w over c minus w is equal to lambda. That is c plus w is equal lambda times c minus w. So c plus w equal lambda c minus lambda w. I distribute the product, and then I bring the term containing w on the left side, and so I've got w plus lambda w is equal lambda c, I bring this c on the other side, minus c. So that 1 plus lambda w is equal lambda minus 1 c. Okay? Well, let me check well the signs. Okay. Good. I need to erase some. Okay, I need this one. So from the last one, I've got that w is equal lambda minus 1 divided lambda plus 1 times c. Okay? But what is lambda? Lambda is equal to all this stuff here. Let's calculate it. Lambda is equal c plus u times c plus v. That is, let's distribute c squared plus cv plus cu plus uv is the numerator, and the denominator is c squared minus cv minus cu plus, because it's minus times minus, plus uv. Okay. Now we are almost done, because what we need now is just simply substitute lambda in this equation here. Let's do it. So W is equal. Okay. Let's call, for simplicity, let's call all this stuff here. Let me do it. No. Let's go on. Let's go on straight on. So we have lambda minus 1. Lambda minus 1 is just, I have to do the common denominator. If I have got lambda minus 1, it is like this. And so I have to do the common denominator, and let me call the denominator then denominator. What I've got this again, that is c squared plus cv plus cu plus uv, and then I've got minus 1 times this denominator here, that is minus, let's do it, minus multiplied by this is minus c squared. Then minus 1 times minus cv is plus cv. Then again plus cu, and then minus uv. All divided by this, that I call then, for simplicity. So c squared minus c squared, they go away. Then uv minus uv, they go away. Let's do the same work on downstairs. I've got lambda plus 1. So again, denominator. And then I've got lambda my plus 1. So lambda plus 1 is again the same. The denominator is here. And so I write again for lambda this one, c squared plus cv plus cu plus uv. And then this time instead of minus I've got plus the denominator, because it's times 1, is plus c squared minus cv minus cu plus uv. Okay, so this time I've got that this one and this one go away, and the same for these two pieces. So all this stuff here is W equal, upside I've got CV plus CV is 2CV, then CU plus CU 2CU, so I can factorize to C, and this V plus U divided denominator, and then I've got all this part here divided all this, so I can multiply by the inverse, and here I've got C squared plus C squared, it is 2C squared plus UV plus UV 2UV, so I factorize the 2 plus UV. Okay, well, this. And at the end of the story, I've got that W is equal to what? To let me divide again by C squared. No. let's write it again like this. C. I can divide by C. Let's write this one. Divided by C squared plus UV. Okay, well, there is a better way to write it. Oh, sorry. There is, I think, yes, there is an error, because here it was CV. To see denominator. Oh, yeah. This is the ratio of lambda minus 1 divided by lambda plus 1. And I forgot that this all is multiplied by c. Okay, so I've got this result, c squared here and c squared here. Okay, well, at this point, what can I do is that with this final expression, I can rewrite it here, dividing by c squared, numerator and denominator. So W is equal V plus U divided 1 plus UV over c squared. And this is the formula, the relativistic formula to add velocities. Do you like it? You should like it, because this formula here tells us that when U and V are smaller, much smaller than the speed of light, the product UV over c squared, let's see, if UV over c squared is much smaller than 1, we are in a classical situation where the velocity are smaller than the speed of light, much smaller, and so this term here is much smaller than 1, and we can neglect it. The result is that V is equal, the W is equal V plus U, is the Newtonian formula. Okay, what happens now? Let's consider another important case. Oh, we know that one of the fundamental assumptions of the special theory of relativity is that it is impossible to go faster than light. Let's see what happens. Suppose that this time, instead of having the tank and the bullet, I've got a spaceship traveling. Here I am on the Earth. This is A, this is B, traveling very fast. V. that is about the speed of light. And then from this starship, a little shuttle fly away with the speed u respect to b. C is flying away with the speed much high, very near to the speed of light as well. So classically, in using the Newtonian formula, you should find that the W velocity of the shuttle C measured by the man on the Earth should be equal to V plus C plus U, that is about twice the speed of light, adding all these, adding together these two speeds. But it is not true, it is not possible, as you know. Let's see what happens using our formula. W is equal V plus U is about 2c, because we know that these are both traveling very near to the speed of light. Let's say that is about 2c divided by what? 1 plus c times c over c squared. But this is 1, so 1 plus 1 is 2, and so this is 2c over 2 is equal to c. So you see that in this case, even if both the velocity are very near to the speed of light, the resulting velocity, the sum of the two velocities as measured by the observing man standing still on the Earth, is always c. It can't be more than c. I mean, about c, around c, because this is just a little bit less than c, because we said that is a big fraction. Suppose that is, if we want to do the things rigorous, we should say that, for instance, this is 90% of the speed of light, and is the same, and this is again 90% of the speed of light. And when we apply the formula using these values here, you have got that the W will be not 1.8 times c, as in the classical formula, but 0.9 c plus 0.9 c, that is 1.8 c, but it is divided 1 plus 0.9 times 0.9 over c squared. Sorry, 0.9 c, 0.9 c, so c squared over c squared. So this is 1 point. Let's do it quickly. It is 0.9 times, silly me, I can do it without calculating. This is 1.8 divided 1 plus, this is 0.81, because 9 times 9 is 81, 0.81. So it is like this. 1.80 divided by 1.81 c. That is about c. Just a little bit less of c. Okay. With this formula here, it is possible to calculate the velocity in all these cases. Thank you very much.